So far, what we have looked at is sizing of ceramics, measuring their porosity and all of that. But a very important aspect now I shall be tackling is chemical composition of ceramics. Many of you have done wet chemical analysis back in your college days, and even today wet chemical analysis is a very important standby mechanism for determining chemical composition. If you are working, say, in a refractory industry where you are developing alumina refractory, what are the things that you wish to avoid over there? Silica, which reduces the melting point, alkaline oxides, which again reduce the melting point, alumina refractory is here, it is 99.9%, let us say. So, by wet chemical analysis, we can easily measure the amount of alumina. But to measure the smaller amounts of the impurities, which is less than 0.1%, wet chemical analysis does not always work. One of the easiest ways of doing a chemical analysis is emission spectroscopy. All of you know that each chemical, if inserted into a flame or a plasma, will emit its own typical color. And in emission spectroscopy, what we do is we do thermal stimulation of electrons, because we inject that into a flame, and what we get is characteristic emission of the cation. In this emission spectroscopy, we can go to at least ppm levels. This is if we are using solids. But if we do, say, flame emission spectroscopy using liquids, means solution, same thing applies, it will be detected up to parts per billion level. Atomic absorption spectroscopy. Again, a thermal stimulation where the solution is injected into a flame. Again, we will have UV or visible light characteristic of the cation, and this is sensitive up to ppm level. An interesting one is X-ray fluorescence or XRF. Here X-rays are used to stimulate electrons. That is, the X-ray beam hits, a electron from a core level is removed, electron from the top higher levels fall down, emitting characteristic fluorescence. This is also sensitive to ppm. Of course, the atomic mass has to be more than 11. In these cases, we get quantitative data. There is another one, infrared absorption. In infrared absorption, what happens is infrared causes the bonds to scissor, to vibrate, to stretch. There are 3 modes, and infrared absorption, where it occurs, is a fingerprint of that particular bond. If I have got carbon monoxide, it will absorb at a particular range, which is different from carbon dioxide. H2O would have a different absorption as opposed to deuterium oxide because of the masses. Hydrogen is light, deuterium is heavy, so it would require more energy to cause the vibration of the DOD bond. And infrared absorption is a qualitative indicator. I would absolutely say a qualitative indicator of what the bonds are. X-ray diffraction. X-ray diffraction. I guess all of you have heard it. In this particular case, we have, let us say, we have got parallel atomic layers. X-ray beams are incident. They are reflected. This particular beam has a longer path length to cross equal to this one. This particular beam has a longer path length to cross this and this compared to the first one. So, there is a phase difference and a diffraction pattern is generated. By X-ray diffraction, you will see how we can do phase analysis of materials. This I will take up at a later stage of today's lecture. So, other than X-ray diffraction, which I have not explained, but I will show you how it is done at a later stage. At this particular point of time, we know how to do a chemical analysis. An interesting way of knowing what is the chemical composition is basically a thermal analysis. This is a very important tool in ceramic processing. Why? I shall come to it shortly. I shall focus on only two: differential thermal analysis and differential thermogravimetric analysis. In both the cases, what we have is a furnace, cylindrical furnace, which is heated resistively from the top. There is a piece of high temperature wire, platinum normally, and this is another platinum support on which two small crucibles are placed. These crucibles can be of alumina, since alumina will not go any change, even crystallographic change up to 1500 degrees centigrade, the maximum thermal operation limit of this equipment, or it can be also platinum. There are two thermocouples embedded at the bottom of this. This particular material, one crucible, is filled with say 10 milligram reference material which does not undergo any chemical or physical change, and in most of the cases alumina powder is used. It does not undergo any change. And in the other crucible, the sample is placed. In this particular apparatus, we measure the del T. This standard reference material would be at the same temperature T as this crucible would be, if under any circumstances. Under normal circumstances, if there is no reaction, then this del T, the difference in temperature between the two, would be 0. However, if this reference material is undergoing any change, then the del T would not be 0. If it is exothermic, it would show higher temperature. If it is endothermic, it would show lower temperature. If it is undergoing crystallization, it would again absorb heat. So, this measurement of del T between the reference and the sample at each temperature would tell us if there is any reaction happening. For example, if this is the temperature scale, room temperature 200, 400, 600, 800, 1000, and it goes on to 1400, let us say, and this is the del T. This is 0. This is negative and this is positive. So, if heat is absorbed as we go up in temperature, it would show this. And after some time, when the reaction is complete, because this heat is absorbed. But at some point of time, if it gives off heat, it would look something like this. Now, this exothermic peak and the endothermic peak is characteristic of this particular material, and we would know what it is. This is what is called differential thermal analysis. In the Reed's book, which I referred to before I left off, or in any other book I had given as references, you would find this in greater detail. This was DTA. So, what is DTG? This beam is really a beam which is supported by a counterweight. So, if during this heat up process, this material loses weight, it will show up. Normally, if this is T and this is W, for ceramic powders, let us say in this case we have taken alumina, so it won't undergo a change, and here we have got, let us say, aluminum hydroxide. Let us have fun with it. So, here we have got alumina and here we have got aluminum hydroxide. So, what would we see? First, as we heat it, as we come closer to 100 degrees centigrade, it loses water. This is a surface adsorbed water. It loses water, levels off. But then, remember, aluminum hydroxide is what I said, and it is a jelly-like substance. It got a lot of chemisorped water. So, it loses all the water and then levels off. So, this is the weight of water which that 10 milligram aluminum hydroxide gel had. If I go to high enough temperatures where aluminum hydroxide decomposes, then I would see a further drop till all the aluminum hydroxide has decomposed. So, this differential thermal analysis, both the DTA and the DTG, both of them tell us at what point of time will these materials really undergo degassing, desorption of water, physisorbed water, desorption of chemisorbed water, and if the material is itself dissociating to give the final oxide over here. This differential thermal analysis of ceramic materials is very important. For example, let us say there are many refractory materials like, say, alumina itself. Alumina itself comes in huge gunny bags. They are all insulated so that moisture does not get in. But in our country, moisture does get in. So, before this alumina can be used for refractories, someone has to do a differential thermogravimetric analysis to see how much of moisture is adsorbed on the alumina surface. Because they may well think this is very dry alumina, measure off a ton and start the processing. Whereas, due to adsorption of the moisture, there could be as much as 10% moisture. So, the amount of alumina would be 10% less, and as a result the final product would not have the alumina it should have and would lead to failure. So, this differential thermal analysis is also very important for determining, characterizing ceramic powders. Well, so far, as a recap, I would say I have covered particle sizing, porosity, density, chemical analysis of the powders. Why are these important? I could have followed the books which are available and gone ahead with a textbook fashion, but I would rather deal with a real life example. One of my students here was working for his MTech project, where his job was slag. Blast furnace slag is a total waste material. Fly ash, burnt product, coal product, very high rich in silica and other materials, another wasteline product. What I asked him was to try to develop a process of using blast furnace slag with fly ash, which are really waste products and are really causing environmental disaster, and adding to it, say, sand, clay, and I said, find out the technique of making a good floor tile so that we can recycle our waste products and have our money back. Now, let me go through the characterization processes he had to go through. So, let's turn to the monitor. Don't look at numbers. You see, I gave him clay. He got clay from 3 different areas, and he had to measure silica, alumina, iron oxide, calcium oxide, magnesium oxide, potassium oxide, sodium oxide. Why? Because this iron oxide, titania, calcium, magnesia, potassium oxide, sodium oxide all cause lowering of the melting point. And because if the melting point lowers, then one of the biggest problems that we face is it blisters. There is a, can you focus on my hand? Yeah, I burned my hand here yesterday. It blisters. Let's go back to the table. This is what we don't want. We want a good smooth product. So he had to determine for each what was the concentration of each of them. As a next step, he had to make different batches. There is, again, there is a huge table, don't worry about it. Somewhere he had feldspar a certain amount. Then he varied the different constituent and made 10 different batches. The earlier batches did not have any slag. The later batches had one type or the other type of slag. So he made those batches. Again, after making the batches, he had to measure the composition all over again. Because, for example, if you take, say, KGP1 and KGP10, what was it? Oh, sorry. KGP1 had clay 2. It did not have any slag, whereas KGP10 at the bottom had slag. So, the thing is, he had to measure the chemical composition for each all over again. And this is why determining the chemical composition of any ceramic system is very important. Because titanium dioxide can lower melting point, alkaline earth metals can lower melting point, and this becomes very important, because here we are worried that if you have got too much of a liquid, that is, if we have got too much of calcium oxide, magnesium oxide, we have got too much of alkaline earth, we will have a high amount of liquid. So, if you look from KGP1, where Al2O3 is to SiO2 is 0.355, there the ratio of the alkaline earth and the alkali metals are 4.76 to the right column. Whereas at the bottom one, we had almost same Al2 SiO3 ratio, but the amount of alkaline or alkali earth oxide was very, very small. So, what he did was, he had to determine the chemical composition of all of these batches, of all the 10 materials, of all 1, 2, 3, 4, 5, 6, 7, 8 different constituents, and the last line is LOI, loss on ignition, means it can be moisture, it can be organics. How much was lost? So, after this he fired it. Now, let me come to X-ray diffraction. What did he see? You see, he fired all the samples at 1200 degrees centigrade. But then he found that this particular one, which is KGP2, had a mixture of mullite, which is given by theta, and alpha quartz. Whereas the one over here is mostly mullite. Because it was a tile-like material, the whole goal was have as much mullite as possible, because then the material will withstand high temperature and also be hard. You see, from the X-ray diagram, from this diagram, all those series of 10 compounds, he determined where was quartz and mullite. It's only in the 9th compound, when he fired it at 1300 degrees centigrade, did he get what he was really looking for, pure anorthite. The reason is this, that if there is quartz, mullite, anorthite over there, the thermal expansion coefficients would be different, and during sintering, the grains would crack. So, his goal was get 100% anorthite, and only when he heated this one to 1300 degrees centigrade did he succeed in getting anorthite. Now, this is done by X-ray diffraction analysis, because anorthite has got its own diffraction pattern. The 2 theta where I by IO will be the highest is just like a fingerprint, and he used the X-ray diffractogram data to determine at what temperature he had anorthite. But with a but, is this method of using such X-ray diffraction pattern for phase analysis above board is absolutely correct, or does it need more refinement? We will deal with it a bit later. Over here, quartz and mullite. You see, one of the things that happens is this, as I shall show in the next structure, these very fine needles are always mullitic needles. This is known to us through historically. What has happened? This is a sand grain. This has melted over here. These grains of alumina have been formed. Over here, there was a large amount of liquid formed. That's why it is labeled as pore. And as the temperature dropped, mullitic needles, these needles are mullite needles, these grew, they interlocked with each other, and this very interlocked structure gives these materials phenomenal strength. Now, where was this picture obtained from? It was obtained by scanning electron microscopy. I shall deal with this, but before it, if I can go back to this picture on the screen, this reference which I have given here, I would give you time to copy it. This is one of the very, very excellent resources, this particular reference, where they have dealt with what scanning electron microscope is, what it can do, and though the URL looks funny, yet I would urge you to look up this URL, copy it down, and look at the reference. It's one of the best articles on scanning electron microscopy for beginners. Due to copyright infringement restrictions, I cannot show the article. I will talk briefly about SEM, but please copy that list down. I would wait. Copy it down. Okay, let's get back to work. So, what is scanning electron microscopy. Let's say this is a sample and electrons are hitting the surface. This is electrons hitting the surface. This is the sample. The first thing that these electrons would do is emit secondary electrons. They would emit back scattered electrons. The energy of each of these is typical of the particular element that is over here. Let's not forget it. This would emit Auger electrons. Again, fingerprint for the particular material it is being heated. This emits X-rays also, because these electrons can knock off an electron from the inner shell. Atoms fall deep into the inner shell, emitting X-rays, and this primary electron beam can cause emission of X-rays. And finally, cathodoluminescence. Each of these electrons, the secondary electron, the backscattered, the Auger electrons, the X-rays, and the cathodoluminescence are very, very typical of the element that is being bombarded with the electron beams. So these can be used as fingerprints for identifying the different elements. All of these are absolutely measurable by suitable detectors. However, getting a quantitative image, getting quantitative data is something not possible. For example, this is the SEM of raw and fired fly ash. I told you my student was working on using fly ash and blast furnace slag to make them usable material as tile. So he got fly ash, looked at the particle size by SEM before and after firing. Before firing, it was perfectly spherical, and after firing, the size changed. Now here you have a link to YouTube. This one is a 6-part talk of 6 minutes each on what is an SEM, how does the SEM work, how are samples prepared, how is measurement made. And since this link is available on the YouTube, I would urge you to watch all the 4 parts of scanning electron microscopy video on the YouTube. I hope you will write the reference down and then have time to look it up. Okay, let's carry on and get on with what we were doing. The SEM image which you see on the screen over here has been obtained from this secondary electron. It's a camera connected. The electron beam rasters over the surface, emitting secondary electrons, and the camera captures all the secondary electrons and then says, hey, this is how your surface is. You have seen the image of the fly ash. This one on your left is fly ash as received. This one on your right is after firing to 900 degrees centigrade. Look, the spheres are all bursting and generating smaller and smaller spheres. What has happened at 1200 degrees centigrade? What has happened is there are some of these small spheres still present over here, but these large flakes, where did they come from? And you see so many flakes over here. What has happened is at 1200 degrees centigrade, this material, the fly ash, the slag, a part of it has melted due to the presence of impurities, which is too uneconomical to remove, and as a result liquid phases had been generated and we are seeing grains with large liquid phases. With large liquid phases. So, using the SEM, we can look at how during sintering particle size evolves, changes. Here is something that another student of mine was working on. This was his nano-sized magnesium aluminate powders, which is done by HRTM, high resolution transmission electron microscopy. I have given you a reference of a YouTube over there. I would urge you to copy this link down and look it up, because this is an excellent 2-part overview of transmission electron microscopy. Please write the link down and look it up on the web, which gives you a pictorial view and a very good pictorial view of what transmission electron microprobe is. These powders which you see are finer or in this scale than 50 nanometers. These are mostly agglomerates. once they have been fabricated, here, these have sintered together to give us a very, very porous material. What we are trying to achieve is take these ultrafine size powders, shape them and fire them to get a very controlled pore size structure, and this can only be seen by SEM. Now, before I take on the next one, how is SEM different from TEM? SEM operates between say 3 to 20 kilovolts, is a reflecting one, but this one, extra diffraction of fly ash, what we had over here. This one again has fly ash mixed with magnesia, and you see that I have the whole thing has been converted to indialite, which is cordierite, a zero expansion ceramic. So, with extra diffraction, what we did was we could determine what are the principal phases. However, extra diffraction alone does not help in doing phase analysis. What is required is what we call Rietveld refinement. Now, this is not the class to go deep in. What Rietveld refinement allows us is quantity phase analysis, crystal structure, lattice parameters, atomic positions and structure factors. This Rietveld analysis, which is beyond the scope of this course, literally tells us which atom is where in which lattice. To give an example, it can be brought down to this, that is this crystal structure, what is the cell size, what is the amount, what is the structure of the mullite in the cordierite. Rietveld can state it, but unfortunately this is beyond the scope of this book. Now, here in SEM, what we can do is, if I look at this diagram over here on the table, if I can look at the diagram on the table, I have said this emits X-rays. How are these X-rays emitted? Using the standard rule, if this is the nucleus, an electron comes in, ejects this electron, leaving a vacant hole here. So, electrons from the higher level will drop in, and the higher level will drop in, emitting X-ray characteristic of the material. Now, we can put a camera over here and determine the X-ray intensity. For example, here in the slide, I have shown again one of my students, and this I want to emphasize, is this is the SEM on your left. What they have done is measured what is the different X-ray emission due to these different elements: oxygen, magnesium, aluminium, silicon and iron. They made elaborate calculations and submitted the thesis. But the stupidity of, or they did not understand where they were going wrong, and I do not pay much attention to SEM EDAX analysis. Why? Look at the surface here. It is so rough. If the surface is rough, then with this parallel beam falling, the X-rays will be emanated in all directions. And as a result, the X-ray he catches at this point, the intensity of it is really different from the others. He just presumed that the surface is smooth. It is not so. And hence, all these X-ray intensities which has been measured at this particular angle is not correct. The only way to do such analysis is through a micro probe, where the surface is smooth and there are multiple cameras mounted to measure the scattering at different angles and integrate it. This sort of an SEM EDAX analysis is extensively used both in academia and in industry, but it is a totally wrong one to use for any academic purpose. You see, I still believe that if I can do a good optical microscopy of a sample, I will know what its composition is. Why? Because each material has its own polarization, has its own refractive index. Sapphire will look as sapphire, it will not be of any other color. If it has any other color, it is due to something else in the sapphire. The ruby will look ruby red and not of any other color. Diamond has to look white, but if it is yellow, it means there are flaws in the diamond. In this optical image that you see is the optical image of the material which was produced here. Here I am inferencing, I am doing Rietveld analysis, but before my student did, I did an optical analysis. Because indolite, I can see here only two colors, one of indolite, the other one the molite, nothing more. So, this told me there is nothing else in the material other than these two. And optical image, this is under a cross polarizer, is the first choice of any ceramist, geologist or a mineralogist to know what material he is dealing with. So, today in these 2 lecture hours, I have covered broadly characterization of materials. Ceramic materials is a vast subject. I have just given some bird's eye view of what goes on. There are books like Reed's book and other books I have talked of where you can get the details. The SEM, I have given you the reference. The TM, I have given you the excellent reference. And I urge you to look at the YouTube to see how things work, which will give you a feel of what it is. Thank you.